In this video, we will use what you have just learned about the electrons that are organized into shells within the atom to explain several patterns of various variables as they occur across rows and down columns on the periodic table. We will examine data and then use our understanding of electron arrangements to explain that data. The first set of data that we are going to look at is called ionization energy. Ionization energy is energy that is required to make a neutral atom into an ion, and it's specifically defined as the energy to remove the first valence electron. So the ion that we would be talking about here is the positive one, formation of a positive one ion by losing one electron. We're going to begin by looking at some data, and this same data can be found on page 361 of your textbook. So if we look at this data here, this is a graph, and on the x-axis is atomic number, so we're basically going along the periodic table, and on the y-axis is ionization energy. So notice as we go from hydrogen to helium, there's a large increase in ionization energy. And then we're on basically the second row of the periodic table. It starts with lithium, and that second row ends with neon. And again, we see an increase in ionization energy as we go across a row. If we will look at the third row, which starts with sodium and ends with argon, again, in general, ionization energy increases across the row. Here's the fourth row, potassium to chromium. Again, we see an increase across the row, but not as sharp of an increase in the transition metals, the D block metals. And we see the same thing here. So across a row, it seems that ionization energy increases. And if we think about what changes as we go across a row, the number of protons in the nucleus gets higher and higher and higher and higher. So that would make sense because as charge increases, according to Coulomb's law, as charge increases, the force of attraction increases in response. So if the force of attraction increases, then the energy needed to remove an electron is also probably going to increase. One other thing that does not change in a row is that we are keeping electrons in the same energy level. So for example, in the second row, all of the electrons that would be pulled out of the atom because they're the farthest away from the nucleus, they would all be in the second energy level. All the electrons that would be removed in an element from the third row would be electrons in the third energy level, and so on. The other pattern that we can notice is we want to look at down a column. So these red dots help us identify these are all the noble gases, which helium is kind of in the second column, but in some ways it also belongs in the very last, the 18th column of the periodic table, along with the noble gases neon, argon, krypton, and xenon. If we look at these elements, the ionization energy decreases as we go down a column. And we can look again at the first column of the periodic table, lithium, sodium, potassium, rubidium. Not as sharp of a decrease, but still a decrease as we go down a row. If we think about what changes in the atom as we go down a row, the electrons are successively higher occupied energy levels. So for lithium, those electrons would be in the second energy level, then the third for sodium, fourth for potassium, and so on. As the electrons are in higher energy levels, higher occupied energy shells, they are further from the nucleus. And so as distance to those valence electrons increases because we're in a higher energy level, the force of attraction gets weaker, and the ionization energy is going to get stronger. Let's write down on your table a summary of what you just heard. So I've summarized here what I said on the previous slide out loud. Across a row, ionization energy increases because the positive charge in the nucleus increases as the number of protons increases in the nucleus. It's also worth noting that the electrons in a row, the valence electrons, are all in the same occupied energy level or energy shell. So charge increases, pulling on each electron, so the force is greater, and so the energy required to separate an electron from the atom is greater. Down a column, the ionization energy decreases because the valence electrons are in successively higher and higher energy shells. The radius is going to be a little bit greater, making the force weaker, and the ionization energy, the energy to remove, would be lower. So that should be a down arrow right there. So weaker force, less energy required to separate electrons. The second trend to consider is electronegativity. Electronegativity is a measure of the ability of an atom to attract electrons to itself. So it's how tightly does an atom pull electrons from nearby and pull those electrons into itself. It is very closely related to ionization energy. So we're going to take a look now at the data for patterns for electronegativity. So here's some data on electronegativity. I always start by looking at fluorine. Fluorine has the highest electronegativity of all elements on the periodic table because it has the strongest ability to attract electrons to itself, and it has the strongest pull on electrons. Notice the farther you get away from fluorine, kind of steps down, the lower the electronegativity gets. But we're going to consider trends across a row and down a column, just like we did for the other elements. So let's take this second row here, 1, 1.5, 2, 2.5, all the way up to fluorine. It looks like it's increasing across a row. Second row also increases across the row. Third row, there's some little anomalies in the D block, but generally also increasing across a row. So it looks like we've got another, like our previous pattern, another pattern that increases as we go across a row. And if we examine a column, 2.11, 0.9, 0.8, 0.8, 0.7, 1.5, 1.2, 1, 1, 9. It looks like here, you see it even more drastically over here, 4, 3, 2.8, 2.52. The pattern seems to be the exact same order as the pattern that we were looking at before, in that as we go across a row, electronegativity seems to increase, and as we go down a column, electronegativity decreases. So like I said, as we looked at the data, the explanations for electronegativity are very similar to the explanations for ionization energy. Both things are measuring a slightly different quantity with different units, but the fundamental reasons behind these trends are the same. So our explanations very similar. When we're talking about pulling electrons into an atom, as we go across the row, those atoms are getting an increase in positive charge, but the electrons are being pulled into the exact same valence shell for all atoms in the same row. So roughly the same size atom. The charge in the nucleus is increasing, so the force on electrons nearby is going to be stronger. As we go down a column, the electrons being pulled to the atom will be added to a higher electron shell. And the higher electron shell is going to have a higher radius, a farther distance from the nucleus, so the attractive force is weaker and electronegativity decreases down a column. The third trend to look at is something called electron affinity. Electron affinity is the energy change associated with gaining an electron, and it's usually negative. But we're going to consider like the absolute value of the electron affinity. What happens to the size of the electron affinity? So again, we're going to take a look at some data. So here we have some data on electron affinities. Notice the values are different. Fluorine's negative 328 kilojoules for every mole, or like electronegativity was measured to be 4. But we have some values here, and notice that as we go across a row, the absolute value of the electron affinity gets higher. So in other words, more energy is released when fluorine pulls an electron into itself, versus lithium releases less energy when it pulls an electron into itself. And the absolute value of the electron affinities gets smaller gets bigger as we go across a row, and the absolute value of electron affinities gets smaller as we go down a column. Again, this trend's origin, the heart of understanding electron affinity trend, is very similar to explanation to the previous two. As we go across a row, we are talking about the attraction for electrons being stronger because fluorine has a lot more protons in its nucleus than lithium does. So it's going to have a stronger force of attraction and thus more energy released when those electrons come into the atom and a bond is formed. We'll talk a lot more about why these are negative, but you will hear me say a lot, when bonds form, energy is released, and you always have to put in energy to break an attraction. These are all negative because we're talking about energy released when an attraction forms, because an electron that's pulled into the atom forms a new attraction with the protons in the nucleus. So I added that trend to my data table. I notice I included absolute value bars because, as I said, the magnitude of the energy change gets higher as the attraction for an electron being put into an atom gets stronger. And I didn't even repeat my explanation of the pattern because it would be very similar to the previous two. But I put those absolute value bar signs there to remind me that this energy change is usually negative because we are talking about when new attractions form. In this case, an attraction between the nucleus of the atom and an electron. Energy is going to be released. The next trend that we look at is the trend for atomic radius. I always find the definition for the atomic radius to be very interesting. It's defined as half the distance between the nuclei for two adjacent metal atoms or atoms in a diatomic molecule. And we define it that way because the edge of an atom is a very nebulous thing. It's not like 1 second you're in the atom and 1 second you're out. And the location of the electrons is always changing. The nuclei are always vibrating to and fro. They're never still. So what we really have to do, it's easier to pinpoint where the nuclei are than the electrons. So we measure where the two nuclei are and call the radius half the distance between the nuclei for two adjacent atoms. And that's how we define the radius. It's easier to define it from where the nucleus is. So again, we'll look at some data. I think this is one of the more interesting and surprising trends because as we go across a row, if you look at what happens to the nucleus, it's actually getting smaller and smaller and smaller. The third row shows the same trend, smaller and smaller and smaller. It gets smaller and smaller as we go across. And that doesn't, at first thought, make any sense because as we go across a row, we're getting more protons and we're getting more electrons. So logically, more stuff, you would think it's going to take up more space. But what happens as we go across a row is that we're getting more charge. We're increasing, just like we talked about with the last three trends, we're increasing the number of protons in the nucleus. And those protons are all centrally located and pulling harder on the valence electrons. So more protons leads to an increase in force. And the atom's kind of a squishy thing. There's a lot of empty space in it. And so as that force gets stronger, the atom is actually pulled, and those edge electrons are actually pulled in a little bit tighter, like a squishy ball or something, so that they are actually pulled closer to the nucleus. And the radius gets smaller. So this trend might not have been what you actually thought. Across a row, the atomic radius increases. Now if we take a look at a column, this one I think is a little easier to make sense of and really pretty obvious. As we go down a column, the number of energy levels in the atom get higher and higher and higher. So for lithium, electrons that are valence electrons are only in the first and second energy levels. Sodium has electrons in the first, second, and third energy levels. Potassium has electrons in the first, second, third, and fourth. And rubidium has electrons all the way filled through the fifth energy level. So as we get more electrons that are not just more electrons, but more electrons in shells that are further from the nucleus and larger, that's what's causing the atomic radius to increase as we go down a column. So this slide includes a short summary of what was discussed on the previous slide. So you might pause and put this in your notes. Across a row, the radius increases because we're getting more protons, but the electrons stay in the same valence shell, and the whole atom is squeezing together tighter and it has a smaller radius. While down a column, we are adding more occupied energy levels because the valence electrons keep going in higher and higher shells. More occupied shells means a larger radius. Now we're going to look at ionic radius, and for the first time we're not going to look at how this changes across a row or down a column. Instead, we're just going to look at how does the size of an anion or a cation compare to its associated neutral atom. But it kind of goes with the radius, that's why we explain it here. So again, let's look at the data. When we look at the graphics here, the first thing that should jump out at you, we're looking at cations first, and the gray shells represent the size of the neutral atom. The maroon reddish shells represent the size of that atom when it loses electrons to become a cation, and it has them all losing their typical number of electrons. So the first column all lose 1 electron, the second all lose 2, group 3A all loses 3. So first we might just notice what the pattern is. Cations are smaller than the associated neutral element. And then we want to explain why that makes sense. Well, if we just start with lithium, lithium has 3 electrons. 2 of them on the first energy level, and the third will be in the second energy level. Well, when lithium loses 1 electron, now it only has 2 left, and those 2 were in the first energy level. So essentially we go from having electrons in both the first and second electron shell to just electrons in the first. We could do the same thing for beryllium. Beryllium has originally 4 electrons. When it loses 2 of them to become beryllium 2+, now those 2 electrons it goes from having electrons in the second and first energy levels to just having electrons in the first energy level. So in all of these cation cases, you will have 1 less occupied energy level in the cation than in the neutral atom, and that's what makes the cation smaller than their associated neutral element. Now to take a look at the anions. So here the gray again is the neutral atom, and the teal represents the size of its associated anion. So here we don't have a case of changing valence shells. So like oxygen has 8 electrons and O2- now has 10 electrons. In both cases, the valence electrons are in the second energy level. We also, but what we are getting here, when we add electrons, we are not adding protons. So the pull does not get any stronger. The electrons are not in a higher occupied energy level, but we have crammed more electrons into the same amount of space as before. So we've added electrons without adding any more positive charge to kind of pull them in tighter. So what that does is we've really just only increased the repulsion between electrons in the electron shells. And when we have more repulsion, those electrons push each other farther apart, and that causes the atom to take up more space. The same thing could be said of fluorine. Fluorine neutral has 9 electrons and 9 protons. When it becomes fluorine -1, we have not added electrons into a farther away energy level. They're still in the second, but we have also not added any protons. All we've added is another electron. So the electron-electron repulsion increases, and then the size of the anion is higher than that of the neutral atom. The last two trends are only included here because they are periodic trends, but both of these should be trends that you're already familiar with. First, number of valence electrons. That is the number of electrons that are in the highest occupied energy level, and those would be the first electrons that would be lost when forming an ion. So first column has 1, second 2, then skip over 3, 4, 5, 6, 7, and 8. And then we also say that in general, the whole D block has 2 valence electrons. So that's a pattern you're already familiar with. And then the final pattern that you're very familiar with from first year chemistry is the charge of ions. So it's the charge lost when, or charge formed when a metal loses an electron, +1, +2, or +3, or when nonmetals gain an electron, and that's -3, -2, and -1. So that's just a quick review of some other patterns that you already know. So now you're going to dig a little bit deeper into the structure of an electron, the structure of an atom, by learning about PES, photoelectron spectra. They are based on what's called the photoelectric effect, and that means that if you bombard an atom with light of just the right energy, electrons can be removed from the atom. So you're going to go from here onto the from shells to subshells class activity.